Hello, this is Nasser Shalain, and today we're gonna resolve two problems to exercise on C Cuda programming. The first one would be is to refer to this code, which is a sum matrix on GPUs, adapt it to integer matrix addition, find the best execution configuration. So here is the original code, which is this one in here. And to give a quick summarize on this code, so this example demonstrates a simple vector sum on the GPU and on the host. Summary on GPU. So this is just a simple vector sum. So this code has a host code and a GPU code. The sum arrays on GPU splits the work of the vector sum across the CUDA threads on the GPU. A 2D thread block and 2D grid are used. Some arrays and hosts sequentially iterates through vector elements on the host. So as we can see, this is the host code. From here, this is where we have the initializer data. This is how we can create our data with the random properties. This is a function of some matrix on a host. So this is the logic for summing the matrix, and this is the another function to check the result of the matrix. So basically, from the top on here is the host code. Now we get into the GPU code. So here where we assign in the threads and blocks and a block dimension um, for the x and y, and here is the IDX for the wrap. And here is the logic on how to print all the else. And here we have the logic for getting the matrix logic. And here we have the main function. And here where we set all the CUDA properties, and we this is where we set up the data size of a matrix. Here we this is where we switch from a host to CUDA memory. This is how we initialize data at the host side. Here is the CUDA calling function to add a matrix at host side for result checks. And finally, here is to again shift the from the CUDA memory to the host. So by using this CUDA copy, which is gonna be transfer data from a host to a device, and then again eventually this is to invoke a kernel at a host side, and here is the step to copy kernel result back to the host side after doing all this logic on the GPU. And here is the finally to check the result and to free the device global memory. This is where we free memory in CUDA. And again, this is freeing a host memory in CUDA. So it's been asked for us to adapt it to integer matrix addition and find the best execution configuration. So I've worked on that, and this is the BN Compare software. This is the old code, and this is the best adoption for configuration. As the requirement, the first step it was to change from float to integer, as we do in here. So this is the first step, and again here is taking integer instead of floats. So this is in doing the same thing in here. Better practice as well for the boolean instead of getting integer, providing a boolean value. And so this is pretty much on the host side. Then eventually we're gonna come to the GPU side. One of our main as well changes is here as well, changing from float to integer. And the same thing here, changing from float to integer. And this is where comes the best execution configurations. Here is to take only the necessary uh, number of blocks and threads by assigning of a dimension of 32, instead of assigning a whole huge, which this number, which is 1024, is the maximum of the dimension in GPU anyway. So instead of you evoking necessary kernels, so we just took the necessary one, which is 32. So mainly this is this changes answering or resolving of one of the way of the best execution configuration on the GPU. So yeah, so at this point we respond to the adaptation to integer to from float to integer, and the best execution practice. Now we're gonna jump to the another problem is to refer this code, make new kernel to let each thread handle two elements. Here it says defends the best execution configuration as well. So again, this is the original code. So again, this is an example demonstrates a simple vector sum on the GPU and the host. Some array on GPU splits the work of the vector sum across Cuda threads on the GPU. A 1D thread block and 2D grid are used. Some arrays on a host sequentially iterates through vector elements on the host. So the same. This is the host code. This is the data initializer. This is some matrix logic. This is the function to check the result. So this is where the host code ends up, and this is where we invoke the kernel. Here we assign number of threads and blocks and block dimension, pretty much the same like as the previous one. So it's pretty much the same as the previous one. And now for the on this code in this part in here, I've worked on the changes. I can this show in here in this Word document. So the main changes occurs in this section here of this one in here, right? So here, this is what is the changes. So here, what we want is to uh, make a new kernel to let each thread handle two elements, and this is how that should be occurring. So here we ensure that we don't get out of bounds. So here we change. Here we have the biggest change on number of threads to handle two elements. Before we used to have a the y's times x plus ax, but here the fix would be to have ay times an x plus ax times two. And here how that is gonna be able to handle two elements. And here we have a code to ensure that we don't get out of the bounds, and thereby setting this condition that we're not getting, we are always in between less than uh, this variable here, or no more than the number of the y's, which is going to be provided here at the function itself. And here we have the logic, and then here we have a second a condition where it ensures second element is within the bounds. And here we have a condition that the thread ID x plus one, since it's started from a zero array, is less than the threads between an x times and y. And then again we provide this logic, but the most important is the condition that we set up, which makes sure that we don't get out of the bound, and making sure we have the second element is within the bounds. So pretty much that's it. This one is responding to this question of make new kernel to let each thread handle two elements. Now to find the best execution configuration, um, this is where we did the change is adjusting the block size. So going back to the original code, I believe that we had that somewhere here. Here when we invoking a cardinal, so we invoking a cardinal with the wrong size of the dimension of x thread, and we using the unnecessary blocks. So the major change in here will be is to change that to the suitable block size. And eventually, since we do that, we have to reduce the grid size by half along. So we as well change here. I believe in here was an x block x minus 1, but we change it instead of 1 to 2 minus 1 because here we are an array. We kind of not missing up the since we having like two elements. As according to this pattern here, we have like two elements for each thread, so we have to change that accordingly. Before we have minus one, now we're doing two threads minus one. That's pretty much for this video. Thank you very much for watching it, and good luck. Thanks.